Okay, so for part 2 of the 2-1 notes here, we'll wrap up the last couple slides of this and the last couple examples. I want to go back and recap a little bit again. This is something that in Physics 1 we did not see a lot of. However, you have hopefully talked about this going back to pre-calc. So what does it mean to be a unit vector? We'll just break up the name, right? A unit vector is telling me that it's a vector that has a unit of magnitude. It's got a magnitude that is truly 1 unit. And so the two easiest examples of a unit vector would be I, which you defined in pre-calc. A lot of the textbooks we'll use an I with a hat over it, or even sometimes I'll just do this. They all mean the same thing. But anyway, when you have that unit vector there, that tells me that it's 1 unit in the positive or negative x direction. So if it's just I, we'll assume it's the positive x direction. So when you see this format, keep in mind this is representing a vector. Right? These brackets here are representing a vector. This is telling me I'm going off to the right 1 unit. This is telling me I'm not going up or down at all. So the unit vector I would look something more or less like that. Right? It would be 1 unit to the right. Similarly, the unit vector j is defined as the unit vector that goes up 1. Right? So again, if it's a positive, we'll assume that it's going up 1. So that unit vector would look something more or less like this. Right, where our vector is going upward. Now in pre-calculus, you actually talked about the fact that you could write any vector, you could convert a vector to a unit vector, or you could find the unit vector in the same direction of that vector, I should say. And so if you remember back, and this doesn't pop up a whole lot in physics, but it's probably just a good math skill to remember. So if I gave you a vector that was 2, 5, right, and actually for my sake I'm going to make those easier numbers. Let's make this 3, 4. How about that? So if I gave you this vector, that would tell me that that vector is going over 3, it's going up 4, so keep in mind these are just the components. The actual vector itself would be this vector right here. Right? Now I chose 3, 4 because I know that that would have a magnitude of 5. Right? So just doing a simple Pythagorean theorem. Well, if this has a magnitude of 5, it's not a unit vector. So how could I find the unit vector that is in the same direction as this? Well, the way that you learned in pre-calc, which is a pretty easy means to do it, is if you know that the magnitude of this vector is 5, then if you just take each of those components and individually divide them by 5, that converts it to a unit vector. So if I take each one of those individually, then 3/5, 4/5 would be the unit vector that is in the same direction as that. So it would be a smaller vector on this diagram here. It would be the same direction. So it would be only 1 unit long, but it would be that same proportion, that same ratio. So again, not necessarily a skill that pops up a whole lot in physics, but probably a good thing to review, particularly maybe for you moving forward with the calc side of things. Anyway, how can you write any vector in terms of unit vectors? Well, that just comes back to, again, if I gave you the example of 3, 4, you could actually write this in terms of I and j. You could write this vector, so if I just call this vector v, you could actually write this as 3i plus 4j, right? Because this is saying I'm taking 3 times my unit vector here plus 4 times my unit vector here, and then I'm, obviously because I'm adding them, I'm just adding the components, which would give me 3 and then 0, and then plus 0 and 4, so I'd get a result of 3, 4. So anyway, making sure you're comfortable with this. You will see this notation from time to time in both class and on the test. So it's always a good idea to make sure you're comfortable with both this notation and this notation. And keep in mind that these don't actually tell me anything directly, right? This just gives me a means to find the magnitude. Okay, so when they represent a vector by 3, 4, they're giving me the components, which isn't the actual vector, but it's a means to find the magnitude and the angle of that vector. So it still conveys a lot of important information. But anyway, that's enough hopefully background on that. A few more examples to make sure we're comfortable with everything. And so this first example here, we've got a rabbit escaping a fox. It's running 40 degrees north of west at 10 meters per second. So again, it's going 40 degrees north of west, and keep in mind this is not bearings. So when it says north of west, it means if I was going west, but then I go upward 40 degrees. So this angle here with respect to the horizontal would be 40 degrees, and then this was 10 meters per second. So that's the situation, that's the setup that we're looking at for this. And then we just need to find the two components, and they want us to write this in terms of a unit vector. So to write the velocity in terms of the components and unit vectors, obviously just finding the components is pretty easy, something I'm sure you guys are all comfortable with. Right? Finding the x component would be 10 times cosine of 40. Finding the y component would be 10 times sine of 40. So when I find those two components, my x component of the velocity would be, I'm going to go ahead and define it as negative 7.66. And again, the negative just indicating it's going off to the west. I could also drop the negative and just define west, which would be fine. And then the vertical component here would be positive 6.43 meters per second because we're going north 6.43 meters per second. Okay, so in terms of the components, I've got it right here. So again, in terms of how I could write that as unit vectors or in a vector component form, I could also write this exact same thing as negative 7.66 comma 6.43, right? So if I define my velocity vector as this, it means the exact same thing as my 10 meters per second at that angle, right? This truly does equate to that. And then I could also write this in terms of I and j, right? So I could write this as negative 7.66i, and the negative is important because that once again tells me the direction, and obviously for a vector the direction matters, so we need to make sure we include that. And then positive 6.43j. Okay, so again, my component forms, and then in terms of my unit vectors I and j, I can break it up this way too. Hopefully this all looks pretty familiar. Again, if you ever do need any additional practice, if you don't feel comfortable with this stuff, just let me know, but I think hopefully probably you guys are pretty comfortable with this already. So anyway, last example, and this one again is one that you've had some practice with, but it's been a little while. So I will go ahead and work this out with you guys just to make sure everybody feels okay with it. But hopefully this is one that if you wanted to pause the video and try it on your own, maybe you could get the right answer without needing me to work it out for you. But I will go ahead and do that, so if you want to continue watching, feel free to continue watching. So the first thing I'm actually going to do for this problem is reorient the picture. You don't necessarily have to do that. As long as you're working with a consistent frame of reference, that's fine. But based on this diagram, I kind of like to reorient it because it wants me to find the net force. In this case, it's kind of acting like down a ramp, which we've seen before. So I'm actually going to just take this and I'm going to rotate my picture to where this is now my ramp going horizontally. So basically I've rotated my picture about 15 degrees about the origin there. But anyway, my force 2 then, so drawing on these three forces I guess, force 2 would be going straight up based on my picture, so 20 newtons. Force 1 is going off at the angle here of 45 degrees, or close to it, hopefully, if my picture is any good. And then force 3 is the one that's pulling down. I know I cut that picture off a little bit there, but force 3 is coming down at an angle. Now keep in mind, that is not going straight down my y-axis because I've rotated my picture. Doing a little basic geometry in here though, right, if I make a right triangle here, I know that this would be 75 degrees because it'd have to be the complement of that 15, which would take this angle back here right back to being congruent with this angle. So the angle with respect to my y-axis in my second diagram would be 15 degrees. So then at this point, finding the resultant, again, a process you guys are very comfortable with, right? You've done this 100 times, probably more than that if you've actually done your homework. So Ashley and Nathan have done this 100 times, and Kenny's done this at least twice. But anyway, breaking it up into the components, right? So force 2, my components for force 2, well, it's not going left or right at all. So if I want to write that in vector form, I'm not going left or right, but I am going upward positive 20. Breaking up force 1 over here, it is a nice 45-45 triangle, right? So because it's a 45-45-90 triangle, I know that once I find one leg, these two legs here are going to be congruent. So that kind of cuts my work in half. So force 1, the components for that would be 50 times the cosine of 45 and 50 times the sine of 45. So when we find that, let's see if I can find my calculation here. You got that 35.4 for each of those components. And each one of those would be a positive value, right? Because I'm going off to the right and I'm going upward. And then finally, the force that goes down, right? So I'd find my third force, the components of that guy. This is 57. So then 57 times the cosine of 15, and then 57 times the sine of 15. So 57 cosine of 15 ends up being 55.1, and I'm going to go ahead and make that a negative 55.1, and whoops, I started to write that in the wrong spot. I want my x component first. So 57 times sine of 15 would be 14.8. I'll still make that a positive because it's still going off to the right, and then here's my negative 55.1 because it's going down. Now if you look at this problem, right, to find the resultant, to find the totals, I simply add up my components. So if I add up my horizontal components, my total force, my resultant vector, if you will, would be, looks like it's about 50.2, right? If you look at our vertical components, well, if you look closely, they almost cancel out perfectly, and that's because if we actually follow the rules of sig figs here, they would cancel out perfectly, right? If I was following significant figures, this would just be 35, this would just be 55, and then 20 plus 35 would be a positive 55, minus 55 would be 0. Okay, so technically if I was following significant figures, which is not a bad practice to do, this would be 0, which tells me then that the resultant, right, the resultant would just be 50.2 newtons down the ramp, because it'd be 50.2 newtons off to the right in my second picture, which again was indicating down the ramp for my first picture. Now if you wanted to include this, if you did actually leave the decimals in there, you would get something like 50.2, 0.3, and then obviously from that you could build your right triangle and go from there. Okay, so with respect to the ramp being horizontal, my resulting force would look something more or less like this, right? It'd be pretty low to the ramp there because I'm only going up 0.3 and I'm going over 50.2. Right, so finding then my angle and my hypotenuse. So if you did find that angle, I think I find that angle to be about 0.34 degrees. So not very much of an angle, and that would be above the ramp, right? That would be off the surface of the ramp. Okay, so again, truly this problem was probably set up with the intention of just being straight down the ramp because sig figs. So if you answered that and then answered that down the ramp, that would be perfect. But if you do this one as well, obviously because significant figures aren't necessarily counted for us, you wouldn't be wrong. You would just have to find that, and then this is obviously going to be very close to 50.2 as well, because that 0.3 really isn't going to do anything when I square it. So anyway, hopefully you guys feel pretty comfortable with our basics of vectors. Like I said, if you do want any additional practice, feel free to come back and let me know. Or if you just want to check the textbook, the online mastering resource, you can go through that as well and get comfortable using that software too, just to get a feel for what this looks like. But anyway, section 1, not too bad. So the 2.1, the 2-1 homework actually goes along pretty well with this section. So if you want to try that, feel free to jump in and try to get that one done.